blast off. All right, so 3.7 differentials is what we were doing. So I don't know if any of you are going into math-based career, but if you are, you'll most likely take a class called differential equations. It's kind of a step off of calculus. And essentially, it'll be like this section, but on steroids. Okay. So you take an entire class based off of that. Okay. Oh. All right. Let me share this page with our friends. Oh, Emilio, good thing you got your mask on. I wouldn't want you to catch anything from me over here. Okay. All right. So definition of a differential is here what it is. It is differentiable. It has to be. So a differential is differentiable. Say that 27 times fast. All right. The differential of x is written by dx, okay? And it's any non-zero. And the differential of y is denoted as dy. So you think about our derivatives we normally do, dy over dx is the differential of y divided by the differential of x, okay? So when we do a differential, normally what they want is instead of you writing dy over dx equals derivative, like we normally do, so normally we would have this equals some sort of derivative, they're going to want just dy on the left side. So since you have dy divided by dx, essentially what they're doing is just moving the dx to the right. So this is a differential, okay? So essentially we're going to do a lot of the same thing we've been doing a lot for the past 4 or 5 months. We just get to move the dx to the other side, essentially. That's all we're doing. All right, so we have quite a few examples that we are going to work through. So we'll start with a being y equals x squared. So if we're writing the differential of y, what we first need to do is find dy over dx. Okay, well, what is the derivative of x squared? 2x. So then I need to now rewrite it as a differential, which means instead of doing dy divided by dx, I'll multiply both sides by dx. You don't have to show that step, and you can just say dy is equal to 2x dx. And so that would be your differential of y equals x squared. Any questions on that? Okay, so it shouldn't be too weird or surprising yet. All right, I'm going to just write as a reminder that this is x to the 1/2. So then I'll do dy over dx is equal to, what is the derivative of x to the 1/2? 1/2 x and negative 1/2, good. So I will, when I rewrite it as a differential, I'm also going to rewrite it with a positive exponent. I'll do it at the same time. And so I can say dy is equal to 1 over 2 root x, or you can do 2x to the 1/2 if you want. You can move it down. And then times dx. Or you can put the dx in the numerator. That is kind of up to you. I prefer mine, personally, just outside of it. Otherwise, I feel like it looks strange. All right. Now I'm going to challenge us.
Teachers, please excuse the interruption. We've had some people come down and ask. Yes, we are still taking donations for those who would like to donate to Graham Hossman. Competition between us and El Dorado very close, coming down to the last hour or so. But anybody who still would want to could just come to the office and give it to Miss Paula. Thank you.
I got more money in my car. Remind me. We better win. All right. So I'm going to jump straight to the differential here. Okay, so that I just got to remember to make sure I put my dx on the other side. That is, you can do that if you want. If it helps you to write it as a regular derivative and then move it over, that's fine too. What is the derivative of 2 sine x? So what is the derivative of sine x? Cosine, so it's just 2 cosine x. You don't need to do the product rule since there's not a variable outside of the trig function. Okay, speaking of product rule, we do have to do the product rule here. Oh, guess what I forgot? dx. What I said not to forget. That's what I forgot. I'm going to go ahead and write this as regular derivative so that I don't have to mess with my dx when I do this quotient rule or product rule, and then we'll worry about it. So product rule says 1 d2, and the derivative of e to the x is just e to the x, so 1d2 plus 2 d1, and the derivative of x is just 1. You can leave it like this, or because you're going to have to put it in parentheses anyways with the dx outside of it, because the dx, otherwise you have to distribute the dx to all things. I am actually going to factor out an e to the x, parenthesis, x plus 1, parenthesis, and then my dx. Otherwise, you'd have to put parentheses here, and you'd still have a dx. So if you're going to use parentheses, you might as well have it factored. If we're going to use it to solve, though, you'd have to factor it anyways. On e, I am going to rewrite it as x to the negative 1 to help me with my derivative first. So then I will have dy is equal to, and the derivative of x to the negative 1 is multiply in front, subtract 1 from the exponent. But then I would like you to write it with positive exponents only. So we should have our differential as dy is equal to negative 1 over x squared dx. Any questions on that derivative? Okay. All right. Last two for this slide. We will have to chain rule this. So if you notice, it's not just sine this time, and the 3 is not outside of it, the 3 is inside of it. So I will have to chain rule it. So we will do our dy is equal to derivative of the outside, derivative of sine we already said was cosine, and then I'll keep the inside the same. And then I'll multiply by the derivative of the inside. What is the derivative of 3x? 3. I'm going to go ahead and multiply that 3 out front instead of at the end. Okay. It should be there when you simplify, so it's kind of a matter. And then just don't forget your dx. Once we move on past this chapter, which is this is the last section of the chapter, so we have a test and review a test and do a test next week. We'll learn something called antiderivatives, so you can actually go back and forth and check your answer. So I would be able to do the antiderivative of this and show myself that I get sine 3x. I would know I'm right. It's kind of fun. All right, last one on this slide. We'll definitely have a big chain rule. So I'll derive the outside, keep the inside the same. 1/2 minus 1 is negative 1/2. And then times the derivative of the inside, which is 2x, good. If you see that 1/2 and the 2, I can go ahead and multiply that through so that 2 over 2 is 1. So I just have 1x. And then when I rewrite it, I'll still put my dx there to keep it accurate. dy is equal to, my x has a positive exponent, so it's going to stay in the numerator. But the x squared plus 1 to the negative 1/2, I'll move down. You have the choice to keep it as a 1/2 power or to write it as a square root. Okay. Since we did one the other way earlier, I'll do this one this way. And I'll still put my dx out front. You'll often see your textbook might even put the dx in the numerator with the x here. So nothing really new, just moving that dx over to the other side. This, though, this is good stuff, and this is new. Let me zoom a little bit. So differentials can be used to approximate values given by a function. And so what it says, if you look, f of x plus delta x, that should be familiar. We did that when we did limits, okay? So if I'm trying to approximate something, but it's not exactly, so I could do f of 2, but it's f of 2.1. Okay, well, I could approximate it because that 0.1 would be that change in x, that delta x, okay? And so it's approximate. If you look, they use specifically the approximation symbol. It's the same as just f of x plus my change in y, which should make sense because if I have a change in x, it's going to have some sort of change in y after I plug it in, okay? Or in other words, we would get f of x plus f prime of x dx. So we would have this is actually the focus of what we're going to use here. Alex?
Are those spelled approximation?
No, the second one is not.
The second one is equal?
The second one is an equal sign. Yeah. And so that's important because if you think about it, look here, dy as we previously stated, is f prime of x dx exactly, because it's a differential. So there's that differential. That's how this ties together. So we'll have our regular plus our differential, which then will give us a good approximation. So we're going to use it to approximate root 16.5, which you might be able to kind of do that slightly in your head, not as exact, but like I know what root 16 is. It's 4, and it's not even close to the next perfect square, which would be root 25. So it's going to be a number really, really close to 4. It's on that side. But that's the best I could do. I wouldn't even know, like, I have no clue. 4 point less than 0.5. That's all I would know. So we can use this to actually do that, and you wouldn't even necessarily need a calculator for it. So what we're going to do is, since we are approximating root 16.5, I'm going to let my function f of x equal root x. Okay. So if you were doing a cube root, you would let your function equal cube root of x. If you were doing a fourth root, you'd let it equal fourth root of x. Then I'm going to say f of x plus delta x is equal to exactly what they tell. And I know we already have it up there, but I want to rewrite it because I want to substitute into it. So exactly what's above, but I'm going to now plug in the information I know. So I know that f of x is root x. And I know that I can calculate f prime of x by just doing the derivative. So the derivative of x to the 1/2 is 1/2 x to the negative 1/2, which is also, for writing it correctly, move everything down except for the 1. Or you can do a square root. That's entirely up to you. I kind of like the square root because we're going to plug numbers in, so it makes it better in my brain, a little bit better. So then in place of this f prime of x, I am going to be putting in that 1 over 2 root x in place of it. And then dx is still there. Okay. So now what I can do is let's let x equal 16. Since that's something I know, I would choose something I know. So if we were approximating root 17, I would still choose x as root 16. I want something close that I know. Okay. So then my delta x, or my dx, is going to be the change, 0.5. So again, if I said x was 7, if I was approximating root 17, my delta x would be 1. It'd be how much it went. So if I was approximating root 18, I would still use 16, but then my delta x would be 2. Okay. So whatever that change is. And so then now I just have to go plug in those numbers. So I'm going to have root x, so root 16, plus 1 over 2 root 16 times, I'm going to write 0.5 as 1/2, so it's easier to do our non-calculator based math with. So we know what root 16 is, right? It's 4. So we have 1 over 2 root 16 is 1 over 8, right? And we still have that 1/2 here. And that's 4 plus 1, 16.
Victoria, can you post your attendance?
Yes. We have 4 plus 1 over root 16. Let me post that real quick. Okay, so then we would need to write it as a decimal, though. So how could I figure out the decimal for 1? I know it's going to be 4 point something, that 1 over 16. Some people know it because it is a somewhat common decimal.
2.065.
Yes. Good job. If you didn't know that, you could actually go and do the division for it, and it wouldn't be a big deal. So if I was doing I would do it this way, and it's not going to go in to it. So I would have to add a decimal here kind of thing, and then you would go from there. Okay. Well, the decimal's there, and you could do that. And we'd have to add another one, which is why it's so far, it has a 0 over there if you wanted to. But it is, if you know what 1 over 16 is, it is. Good job. And that is the end.